Hello all, today we're going to learn how to find displacement with a given acceleration and a time. Picture this scenario. Sometime in the future, there are space explorers and they land on this moon and they want to test for gravitational anomalies. They come up with this experiment. They're going to take a small probe and they're going to launch it and they're going to see how long it's going to take for it to leave the sphere of influence of the moon. It has some futuristic engine, so it doesn't affect its mass as it burns, and it's going to be accelerating with accounting for the gravity of the moon. Is going to be accelerating at a constant rate of 1.5 meters per second squared. And after 6 minutes and 42 seconds, the probe's accelerometers detect that it's left the sphere of influence. There's no atmosphere, no rocket equation. We want to find the distance to the edge of the sphere of influence. There are several ways we can do that, but first let's see what they're asking. The question is asking that for us to solve for displacement, it's giving us an acceleration of 1.5 meters per second squared. It's giving us a time of 6 minutes and 42 seconds, which we can convert into seconds for 402 seconds. And we want to solve for d displacement. We know that, well, let's put it this way. We know that the acceleration, the second derivative of the displacement is acceleration, right? And the first method is going to be integration, since there's derivatives involved. And let me draw you 3 little graphs to demonstrate what we're going to do. The first graph is going to be displacement over time. The second one is going to be velocity over time, and the third one is going to be acceleration over time. Now, since this probe left the ground and it's now accelerating, the displacement, the distance, is going to be a quadratic. If we take the derivative of that, right, we're going to get a linear slope, which is going to be our velocity. Our velocity is going to be changing at a constant rate. And if we take the derivative of that, we're going to get a constant. The velocity is changing at a constant rate of the acceleration. Now we know the inverse of derivation is integration. So if we want to find the area under the curve of the acceleration graph, that'll give us the slope of the velocity, and doing the same for the velocity will give us the slope for the displacement. And we're given that our acceleration is 1.5 meters per second. So our displacement will be the double integral, or a double integration of our acceleration. We can use technology or calculator, graphing calculator, to find out what the double integral will be. That's 0.75 x squared, and this is the function of the displacement that we got from a double integration of the acceleration. The x is actually the t. All we have to do is plug that in. We'll get 402 seconds squared times 0.75, and we'll get 203 meters, sorry. We can do it actually a second time with a displacement equation if we don't want to do integration. We know that the delta d equals the displacement equals the velocity times time, and the velocity is acceleration times time. We can derive this formula from it, where the delta d is displacement, the vi times t is the initial velocity, which is 0, so it doesn't count on our equation. It started off of the ground, and we're given the 402 seconds and the 1.5 meters per second squared for the acceleration. All we have to do is plug in the values that we have. 0 for initial velocity, and the t, I miswrote that there. That should be 402, but it's multiplied by 0, so it doesn't matter anyway. We have 1/2 times 1.5, which is our acceleration, times the time squared, and we get the same answer. Now, we can solve it a third way. We can solve it graphically, and this is kind of a nice representation just to see what's happening, and to prove and kind of show what the displacement graph actually looks like off of the second double integration. We can, in the A column, I made an input table that is our times, our seconds, and I wrote the function that we got from the integration in the B column, and I dragged that down. That's by second how much the probe has traveled. And just for the sake of it, to show you that they are equal, I'm going to quickly write the formula that we got from the equation. And that's going to give us the same value. Let me track that down real quick. This is just proving that they're equal, that we found the same answer, but let's find it real quick. Age 402, because it's our seconds, and at 402 seconds, that is our distance traveled. Now to solve this graphically, I'm going to create a quick line graph and struggle to create a second graph, and then decide since they're the same, I'm not going to do that anyway. But from here, now that we have this graph, we can take and go down the x-axis, which is our time, and the y-axis, which is our displacement. We can go down the x and find 402, and that will give us, that intersection of the y-axis will give us the displacement that we have traveled. So it's a pretty small move, but I hope you learned something today. I actually want to go get some sleep, so peace out.